Now in this 18 plus this, we have 18.857142. After that, this 6 in this 6 by 7, in place of this, we can again substitute this whole thing, and you can clearly see that the digits 857142 are going to be repeated again and again. So that's what we write. By the way, have you seen where we have used the pigeonhole principle? We have used the pigeonhole principle there in the fact that there are only finitely many remainders available to us, and we are continuing the process every time we are getting a remainder. So at one point we are bound to get a repetition. That's where we are using the pigeonhole principle. So using this, again and again, we get the as this 18.857142. Then again 857142. And then again that, and it goes on like this. That is the block of digits is repeated over and over again. Okay, now the objection that this is not a general rational number but it's a special rational number, it can be answered like this. In concluding this thing and in considering this example, we have actually not used any special properties of these parts of the number 132 or 7. We are what we are doing, we are just going on applying the Euclidean algorithm in a particular way every time we are getting a remainder, and the fact that the divisor stays the same makes the list of remainders finite. So after some stage repetition will occur. That will ultimately lead to an equation like this, which can be used again and again to obtain the decimal expansion of the original rational number. So that's why a block of digits will be repeated. If you want to write this whole thing generally by considering P and Q, you can do that. You have to keep in mind that there are some, of course, although we have considered things in general, but we have not actually seen all the examples yet. This is only one example where the repeating blocks have started appearing just after the decimal point. It did not take any time at all. Once the decimal point has been reached, after that we are getting the repeating blocks. This may not happen in the general case, and that's what that is something we need to address. So here I have written, instead of six getting repeated, we could have had some other remainder repeated. When that happens, the repeating block appears after some digits after the decimal point. For example, that is, the repeating block does not appear immediately after the decimal point. There is a gap. The decimal expansion of, there is a number with huge numerator and denominator, 2047 divided by 1980 is 1.03383838, etc., where repeating block 38 appears after two digits after the decimal. Okay, so this case has also been seen. I mean, if you want, you can find the decimal expansion the way we have done, but that's not the point. The point here is that this can happen. Okay, and the case where the repeating block is appearing just after the decimal point, this is a special case. This is the general case. It can appear quite far away from the decimal point in general. But there is something more we have not addressed, namely the case where the remainder 0 is appearing. Here 0 never appears. What happens when 0 appears? Okay. Next, example where the remainder 0 appears. Let's determine the decimal expansion of 25 divided by 4. So this is somewhat small. We can carry out the process here, although not in a detailed manner like what we did in case of 132 by 7. Somewhat more sketchy. First of all, if I apply the Euclidean algorithm, what do I get? 6 times 4 plus 1. So this gives me the integer part immediately. 6 plus 1 by 4. That 1 by 4 I can write as 1 by 10 times 10 by 4. Now this 10 can be written as 2 times 4 plus 2. So I get 6 plus 1 by 10, 2 plus 2 by 4. 6 plus 2 by 10 plus 1 by 10 times 2 by 4. I can write one more step here itself, and that is I can divide and multiply by 10. Now at this stage I get the zero remainder. 6 plus 2 by 10 plus 1 by 10 square. Now this becomes 5 plus 0 by 10. If okay, there is no need to write within brackets. 0 by 4. That means ultimately this becomes 6 plus 2 by 10 plus 5 by 10 square plus 1 by 10 square times 0 by 4. Here if I use the Euclidean algorithm to write 0 as something times 4 plus some non-negative number, that has to be of this form. 0 times 4 plus 0. There is no other choice. And that's why once we hit 0, then 0 gets repeated again and again. Okay. So or we can, since we have said it, we can write it as well. After this stage, the remainders are all equal to 0. So the decimal expansion of 25 by 4 is 6.25, 0, 0, etc. Okay, so we have considered all the possibilities when our rational number is positive. And if it is 0, then of course nothing there is there to say. It's just 0. But what about the negatives? There are the negatives also, right? Thus, we can conclude this part like this. Thus, occurrence of zero remainder makes the decimal expansion end in an infinite string of zeros. Okay, now the final point. What happens when our rational number is negative? Finally, when our rational number, say p by q, we can consider it like that, is negative, applying the Euclidean algorithm with P by Q is negative. Okay, how can I express this fact? Applying the Euclidean algorithm, or is negative with P less than 0 and Q greater than 0, then any negative rational number can always be expressed like this, where the negative sign can be considered to be with the numerator and denominator is positive. Then applying the Euclidean algorithm once at the very first stage, we get a non-negative remainder, because the remainder that we get will be non-negative. Then it's just like above. Because once we get a non-negative remainder, that's it. The negative sign goes with the integer part, and the remainder, of course, the number as a whole is negative, but the negative sign is taken care of in the first application of Euclidean algorithm itself. After that, we calculate just like we have been calculating here, like above. So what one has to do if one wants to write a general solution? Instead of taking these examples, one has to consider the cases separately, where one would consider general rational numbers, but additional assumption will be that, say, the repeating block appears after this many digits. We have understood the reason why a block gets repeated. The rest is just a matter of writing the thing formally. But I think this is enough for a solution. Now, the solution is over here, but there is one more observation which is somewhat interesting. But before that, let us summarize this. From the above discussion, we see that of a general rational number must become repeating after some stage. And that's what we wanted to show. But something else has come out of this discussion, something extra. Note that the length of repeating block of digits does not exceed the size of the denominator. This is an observation which is somewhat interesting. The repeating block that we are getting, its length means the number of digits in it that will not exceed the size of the denominator, the divisor. That is because we are dividing by that number and the remainders are determining the block of digits that gets repeated. So its length can never exceed the size of the remainder, the size of the divisor. Okay, so with this observation and everything, the set of exercises, the first set of exercises in ring theory is now over. So after this we will start homomorphisms, ideals, kernels of rings, those things. So with this I end this video. If you are new here, please subscribe to my channel, A Mathematical Room. I also have a Facebook page with the same name. You can like that. Sometimes I post some things about mathematics there. You can discuss with me on any type of topics in mathematics there, or you can mail me. The mail address is also available in the channel. So with this I end this video. Have fun with mathematics and do ask questions, okay, in the comment section. I would like to answer them to the best of my ability. We can have lively discussions. So this is me, Lucifer, signing off from the Mathematical Room. Have a nice night.